All right. Good evening. Um, who is there? Nobody. Oh my gosh. This chat room is as empty as the room that I'm in now. Good evening, everyone, or good morning, or good afternoon, or whatever time you're accessing this chat room. This is Celso Batalha, Evergreen Valley College, ch10, and few basic informations, very important. We have an exam this week. So on Thursday, we have exam number 2. Just show you this. Hadi is joining. There you go. Good to see you there, Hadi. It's always good not to be alone in the universe. I hope you can hear me, and I hope you can see my window too. Should be able to. But anyways, so I was mentioning this week we have an exam number 2, and it's gonna be similar to what was exam 1 in the sense that Wednesday night I will open exam number 1 or number 2, and you have 1 hour to try the exam, and then the exam is going to be closed 1 hour later, and you can choose any time on Thursday, and then Thursday midnight is going to be closed. I will allow a second attempt, not necessarily you see the same questions on Saturday. Again, the same idea. Friday night, the exam is open, and you have the entire day to choose 1 hour or so to do the exam. Students who are enrolled in the DSP program should email me so that I can send to them password access to the exam, so they have the rights of double time. And the chapters are, I need a drum. So it's basically comprehensive, but I will be focusing on everything that happened after exam 1, and that includes laws of motion, which is chapter 3, but primarily chapter 4, telescopes and light, chapter 5, formation of stars and terrestrial planets and Jovian planets, basically, and the giant or gas and ice-like planets of our solar system. Okay, um, and pretty much that's it. And then and then today we are entering the realm of stars, and we are learning primarily um, how can we determine information about objects that are so far away that we don't have the means to embrace them with our senses. I mean, remember, we are studying a science-based course, right? And in science, one of the main aspects of science, everything that science developed, the knowledge that science built, is based on the scientific method. And one of the links in the scientific method is the ability of collecting data. So you go out in the field and then you observe something that indicate the existence of an empirical law, and then you go on and collect data, right? So you collect data because you want to evaluate um, the regularity or the physical aspect of your object. So you have either to touch it, to smell it, to measure, to weight. So you have to do things with the object. You have to manipulate in another way. You have to use your senses to um, to cover it. I have a question here. What's going on? Chapter 4, 5, 6, 8. How about chapter 10? What is chapter 10? No, my friend. Chapter 10 is today, this week. Look at that. Chapter 10, measuring stars. If you want, I can put those questions specifically for you. How about that? Just on your exam, are you add no? Yes, yes. Just be happy. Just be happy. It's gonna be everything up to chapter 8, but with more emphasis on chapter 4, 5, 6, and 8. Okay, I will emphasize that. Chapter 4 is crucial. It's about light. In fact, chapter 10 has a lot to do with chapter 4. Um, okay, so it's important. You have to know that. So, but chapter 10 is not part of it. Now I don't know where I am. There you go. Okay, so so in the universe, how can astronomers talk about objects they never collect material from, like quasars or galaxies or stars? I mean, we know the sun. The sun is quite close. Not so close. We haven't been there, but is relatively close. Is I mean, we can even resolve the diameter of the sun and observe details in its surface. And we are going to study that. So the sun is relatively close. We haven't gone there yet to collect sun material, although we received here on Earth, and we are embedded and we are surrounded by solar wind. So we do receive particles the sun itself emit and produce. But talk about any other stars, we have not. We haven't gone to any star system besides our own. We have brought materials from the moon. Perhaps we have Martian material on Earth, but we have collect, pieces of asteroids and pieces of comets and brought to Earth for analysis. But outside our solar system, and not even don't think about it. We haven't collected. So how do we know? How can we be certain that everything we say about quasars, about galaxies, about rotation of stars, how about, I mean, everything we say about star collisions, black holes have some sort of a reality and is scientific in a way that we call us scientific enterprise here in a science such as biology or um, physics done in the laboratory and all of that. How can we do that? So the key to answer this question is, well, we know a lot about light. I mean, we haven't gone to these places, but all these places have been sending light. Since the very beginning of the universe, all these objects have been sending light to all places. And when we are able to observe objects, by observation, we mean we collect light that interact with these objects. Now, interaction of light with matter, and when this happens, I got it. So when light interact with matter, matter imprints on light characteristics of itself, like uh, temperature, the state of the gas, the thermal state of the gas. Is there strong magnetic fields in it or not? Is there rotation going on in the star? So all of that information is somehow imprinted in light that lives or interacts with this object. So when you observe things with telescopes, astronomers, what they really do, they use two basic techniques called spectroscopy and photometry. Spectroscopy and photometry to assess physical properties of celestial objects. So photometry is a technique by which astronomers measure the intensity of light on specific color bands, on specific spectral regions, and by determining how sometimes the ratio between those intensities, astronomers can determine the metallicity of the gas responsible for that light production, or how hot that gas is and how transparent that gas is. And also, photometry is a technique that was very successfully used to determine and to find exoplanets. When exoplanets cross the disk of parent stars, it produces a dimming of the, the, the stellar light. And by measuring the dimming of that light, astronomers can infer properties of planets. Um, Spectroscopy is a different technique. Is when astronomers take the starlight or the galaxy light or the quasar light and create a rainbow of it. And by creating a rainbow, they can study with details what we are going to see in this chapter is called transition lines. I'm not seeing a screen. You're not seeing anything? Oh, I haven't started yet. I'm just in the prolegomena. Can you see this October 26, chapter 10, measuring lights, exam 2? Can you see that? Okay, okay, that's what I am. I'm kind of behind today. I'm too slow, Joe, today. I think it's Monday. Okay, so let's take a look at the slides quickly here. First of all, distances. How can we check distance? And in fact, this is, why, now I remember why I brought this in place. Let me go back there. So besides exam, I recommend that you go through the flashcards again. It's a nice resource. Brightness. This is very important to know what brightness is and the difference between brightness and luminosity. I'm going to write here. Luminosity. The difference between brightness and luminosity. Those two quantities are different. Brightness is how much of the stellar source we observe. So what's the brightness of a star that as you look up to it, you detect with your eyes? We can use instruments to measure that brightness. Now, brightness is different from luminosity. Now, luminosity is something different. Luminosity is the total energy the star itself is producing and sending out. So these two quantities, luminosity and brightness, they relate to each other. And I will write here just for you to follow. Brightness is equal to the luminosity of the stellar source divided by some funny number, 4 times pi. Pi is a number, 3.1415 times distance to that source square. So if you have the luminosity of the star, which is sort of a power the star has, is how much energy the star is producing and sending out every second. So if you take that quantity and divide it by 4 pi distance squared, distance to that source square, you have the brightness as you observe here on your telescope. And then that brightness is later transformed in a system of magnitude that is logarithmic. And then the numbers are used and compared with a group of stars that are supposed to be standards. And then the magnitude system is so developed. I will go over that in a second. But brightness and luminosity are important. Let's see what else here. Stereoscope, you can ignore that one. Parallax is important. We're gonna go there now. Parallax is a technique that allows astronomers to measure distance using simple triangulation. You have to use now space technology for that, but allows to measure basically distances. So you don't need a ruler to go there. Arc minute is a unit of angle. So 1 degree has 60 arc minutes, and 1 arc minute has 60 arc seconds. So arc minutes and arc seconds are not units of times, but angular measurement. So arc second, there you go, I just said it. So this is important to know. Parsec is a unit of distance. is converted to light year as about 3.26 light years. And light years is how much light travels in 1 year. And the speed of light is about 300,000 kilometers every second per second. Don't worry about this. We are not doing calculation. Apparent magnitude. Apparent magnitude is important. Is that magnitude scale um, is the magnitude scale upon which stellar brightness, the brightness that I just defined previously, is converted to. So the magnitudes are such that big numbers indicate faint objects and smaller number indicates bright objects. Like you can see up to magnitude 6. In a good night condition, if you have good eyes, you can see up to magnitude 6.5. But for instance, Venus sometimes so bright in the sky that the magnitude, Venus magnitude, is almost negative point 1 point something. Let me check Venus Venus magnitude. Yeah. Oh my goodness. Negative 4 point. No, wait a second. What is Venus? No, this can't be. Sirius is so bright, it's the brightest star in the sky. The magnitude is negative 1.47, and Venus has magnitude that varies negative 3.7 to negative 4.5. So negative means it's very bright. How about the apparent magnitude of the sun? Is the brightest object in the sky. Is a very small number, negative number. So as you go to smaller numbers, you are probing brighter objects. Okay. So for instance, Hubble telescope can see objects magnitude 30. So 30 is a big number. So it's a very faint object. Okay. What is I'm seeing Moodle? I'm seeing Moodle screen not proper. Okay, got it. All right. So much with flashcards. So apparent magnitude, absolute magnitude is a measure of energy. Basically, is how much bright an object should be were it placed at about 10 parsecs away from us. So you take, for instance, the sun, and you put the sun 10 parsecs, which means 32.6 light years away. What would be its apparent magnitude if that were the case? And then you would have a number. That is the so-called absolute magnitude. Why we use this scale is to compare and to build, as we will see later, HR diagram, Hertzsprung-Russell diagram. Surface is the top of a star. Filters, we are going to see the color filters. Ground state when we talk about atoms. Excited states when atoms are excited. Emission spectra. So now we are talking about spectroscopy. Emissions, transitions. So all lines, all atoms, they have electrons in orbital clouds. And these electrons, they cannot be occupying any particular region. In fact, quantum mechanics forbid this idea of locality, of having particles in places, is more of a sense of probability of determining a particle in a given location. And this applies also for electrons that happen to be orbiting or happen to be associated with atoms. So electrons, they have a certain probability of occupying certain orbitals. But electrons also change their position from orbitals to energy levels, to a different energy levels. And this can only happen if the atom absorbs or release energy to the environment. And by doing so, we have now some interaction between light and matter primarily. So spectroscopy exists because of this interaction between light and matter. And absorption lines and emission lines, or absorption spectrum or emission spectrum is the rainbow that is built up once light is spread out in its different colors, and then you can determine transitions, and by doing so you can figure out what's metallicity the stars have, how hot it is, how fast they rotate, all kind of things, and I will kind of talk about it in a second. The strength of light, spectral lights, and let's just move on. Okay, so check your flashcards is important, and the discussion this week is about distances, basically. Okay, astro discussion, how to measure astronomical distance if the ruler is too short. How do we get distances to galaxies, for instance, or distance to objects we had never been there? This is one of the main points of this class, okay, of this chapter, not this class. And then don't forget we have exam. So let's go through the PowerPoint quickly. Where is the PowerPoint? Right here. Parallax. Look at this. Imagine, so you know for sure the celestial sphere does not exist. So we don't have a kind of a, how do I do that? Wait a second. Let me expand this PowerPoint. Remember, I always have trouble trying to write in a PowerPoint. No, I want to get this guy here. How do I, oh, wait a second. I think I have to save just a second. Get this file, export as PDF, chapter 10. Now let's put this in documents. Just a second, downloads. Okay, just a second. And then I go. File open. Now in documents, right there. And there you go. All right. And then you want to make comments. Enable editing. Okay. All right. So, our galaxy is, is a spiral object. Right? So it has a bulge in there, like a knife. No. So, man, this is such a bad drawing. So let me put like this. There you go. This puts only two arms. So let's say when you go outside in the night sky, so if our galaxy has our location in respect to the center of the galaxy is about 30,000 light years. We're going to learn that later. So what we see in the night sky, so if you go outside now and look up to the sky, you're going to see a very small region around yourself up to, at the most, 3,000 light years. So 3,000 light years, think about the distance from where we are to galaxy center, 30,000 light years. So we see, almost nothing of the galaxy, right? And that's what we see out there. So celestial sphere really doesn't exist, but we have the impression that stars are all at the same distance from us, especially if you go in a site that's completely dark and just place yourself in the floor and then open your arms and look up to the sky. You're going to see kind of this dark thing above you with the stars in it. And then you think you're surrounded by this kind of an imaginary sphere or semi-sphere, and this is not true. I mean, stars are all at different distance from us. So imagine that there is a star A, it's right here, and there is a star B that is further out. Okay, and furthermore, imagine that you have Earth today with a distance of 1 AU to the Sun, 1 astronomical unit to the Sun. And then you look at star A, right? So you look towards star A, and you're going to see the star A somewhere project in this position. But the field where the star A is surrounded by a bunch of stars, right? At all different distance. So that when you take a picture of the star A against the field of stars, you're going to see something like this. Does that make sense? And then do the same exercise today to star B that is further out. So star B will appear right here. It's a square. It's kind of a square star. It's a strange star in the universe, all square. So that's star B right there. And star B is right there. The blue is the star right there. Okay. Now here's the field of stars. They are so far away, right? A, B, C, D. So you have a bunch of stars very far away, but your star A is here and your star B is there today. Now, Earth goes around the sun and keep orbiting and orbiting and orbiting. And then 6 months later, somewhere here. So what do you do next? Now you observe the same two stars again. Now star A, in respect to the field of stars that are so far away, will appear to be somewhere here. So your star A moved in respect to the field of stars to a different position. Same thing, your star B, when you look at star B moved, but not as much. See that? So star B moved, the square star, moved just a little bit in respect to star A that moved much more. So stars that have this displacement with respect to the background stars on a time frame of 6 months, so the stars who appear to be drifting longer, they are closer to us than those that are further out. And the stars that are so far away, they don't drift at all. Just using parallax technique, you cannot detect their motion. So this was conceived a long time ago by Greek philosophers. This is not something new. It was attempted to be detected, but there was no instruments at that time to detect that. But look at this. This displacement in the sky, you can measure if you have precise instruments. So it's a certain amount of arc seconds. So if you go outside and you keep your hands, your arms at arm's length, you make a fist. See if I can make a fist. Is this a fist? It's kind of a fist. Let's see. 1, 2, 3, 4, 5. That's the thumb. That's a perfect. So we have a fist, right? You make a fist with your hand at arm's length, so your arm should be straight. And then you look straight across your fist. This is pretty much 10 degrees in the space, well, more or less 10 degrees. So how do you measure that? Well, you take the size of your hand, the length of your arms. So this distance divided by that gives you 10 degrees, gives you the angle. So which means you can determine angular separation in the celestial sphere, in the sky. So and therefore, so if you have a bunch of stars that don't move, you can come over here and measure how many arc seconds this motion, this apparent motion was, and how many arc seconds this apparent motion was for star B. Now look at this. Now let's bring geometry. If you like mathematics, that's your time now. So if you take this angle right here, tangent of this angle, if you remember your geometry, I know you guys are getting all excited. Tangent of this angle is equal to this distance, especially for a small angle. Tangent is equal to the angle in radians. So it's equal to this distance, which is what? 2 times the stellar radius, or the solar radius in this case, divided by d. D is the distance to the star, right? Right? So what is defined is 1 parsec. So 1 parsec is 1 parsec is the angle 1 arc second. See, 1 arc second. So if this distance here, if this angle, I'm sorry, if this angle is 1 arc second, 1 arc second, if this angle is 1 arc second, this angle is going to be given by 1 astronomical unity, which is the distance, average distance of Earth to the Sun, divided by the distance to that star A. So the distance is then 1 arc second, right? The angle in radians divided by, no, I'm sorry, I'm doing wrong. Oh, let me erase this. Oh, I didn't erase completely, did I? No, I did. So the distance is going to be, 1 AU divided by 1 arc second, and 1 arc second in radians. Now, if you so let's go move it again. So let's go back and see how this plays in the real thing. Wait a second. See, now I have a good drawing here. So 1 arc second is defined by the ratio of 1 AU. So the angle is 1 AU divided by the distance to the star. And the distance to the star is given as 1 parsec, which is 3.26 light years. So if you take the angle and you make it half of that one, so half arc second, half arc second. So the distance is going to double. The radius is the same, but the distance double. And that is going to be 2 parsecs, or 2 times 3.26 light years. So when you measure angles or parallax in parsecs, you in fact have the means to determine the distance to the star, but you have to measure the angular separation of it somehow, and nowadays we use space technology for that. Let me see, where are you now? So brightness, remember we defined that with respect to luminosity, right? So here we have one star that is about 1 parsec away from us, another star that is further out, 2 parsecs, and another star that is 3 parsec, okay? And the stars are such that when you observe them, 1, 2, 3, the yellow, the red, and the blue, they appear like this in the sky. So the blue star appears to be less faint than the yellow star because it's further out. It might be more luminous, but it appears fainter because it's further out. So luminosity is energy. Think about luminosity as energy. Sometimes in some books, our book does that, it calls intrinsic brightness. Not the one you observe, but the one you actually measure. But basically luminosity, brightness is luminosity divided by some number, which is 4 pi times the distance to that object square. So this is the so-called is the result of inverse square law. Inverse square law. So as any light source, when it produces radiation, the light source spreads out in such a way that the intensity of the wave front falls as the distance grows with the square of it, with the square of the distance. So and the apparent magnitude scale, which runs in such a way that, for instance, you have these 3 stars or 4 stars, and then you want to find which of the following apparent magnitude indicates the brightest object in the sky. So then you survey the numbers, see which number is the least one, is the smallest number possible. So D with a -3, so if you put in a scale, you have -3, -2, -1, 0, and then 1, 2, right? And then 3, and so on, so on, so on. So -3 is the smallest possible number and indicates the brightest object, as opposed to 3. 3 is an object still bright in the sky, you can see it, but is the faintest of this set of objects. Okay, that's how the apparent magnitude goes. Now let's talk about spectroscopy. So, and when we talk about spectroscopy, how do we know so much about the chemical composition of stars, how fast they rotate, and all of that? We learned Doppler effect before. We know that Doppler effect is the result of a changing frequency caused by the relative motion or the relative velocity of the source producing the light and the observer. So when the observer is moving towards the source, then we detect what's called a blue shift, the transition change to the blue to a shorter wavelength or high frequency. And when the source or the observer moved away, the source moved away from the observer or vice versa. So when they are splitting apart, we detect a shift of these transitions towards the longer wavelengths. So it's a red shift called red shift. So this we can understand only Doppler effect if we understand spectroscopy. So how spectroscopy can help us to measure properties of celestial objects. So let's take, for instance, an atom that has a nucleus and has an electron cloud. So in the nucleus you have protons, perhaps some neutrons, and the cloud is a probability of finding electrons in a given location, somewhere here. So in a classical sense, that's how I learn in the classical sense, but not in a modern sense. This is not a good way of saying. If you provide energy, like you send light to your atom, so you give energy to your atom or you collide your atom with some other gas, this atom now will become what we call excited, which means it's going to get energy because either you shine light on it, or you allow for collisions. And so the electron or the atom get excited if the electron jump to a further away orbit. And then we say the atom is excited because absorbed energy by sending an electron to an upper orbit. Okay, so that photon of light, that energy was used up to move the electron to a more energetic region. But the atom stays excited just for a short amount of time. So depending on which transition you are talking, time is very small. And eventually this electron goes back to its lower or less energetic orbital. And when it does that, the atom sends out a photon of light with a frequency that is characteristics of that transition. So, in other words, how spectroscopy works. So let's say you have a cloud with a bunch of atoms in it, and these atoms, they are well known for absorbing radiation of a given wavelength. So this radiation goes to the cloud with several other radiation, right? But only this radiation and this other pass through because this one was used up, was absorbed by these little elements, either molecules or atoms. Which means when you observe a spectral distribution that comes out of a source, let's say you have a star right here that produces a spectral distribution of energy. So some energy divided by its frequency. So the frequency characteristic of this transition of this the frequency characteristic of this color, if you will, got absorbed by the atoms or molecules in that cloud, and as a result you have an absorption line. So you have a depletion. This energy right here, that you should have is gone. It's right there in this cloud. So it was used up to warm up the cloud, to excite the molecules in there, to do all kind of things. It got used up by the cloud. So eventually, sometimes the cloud remit back, but not in the direction the radiation was going, but remit back in all possible directions. So this interplay between light and matter is what enables astronomers to infer properties of celestial objects without really going and visit these objects. Okay. So this section explains atoms as having different energies, and then I think I have one of the extra credit activity. You have to go through one of these astro tours and then follow the transition in there. Here's a better description of what I was showing. So you have a cloud, right, that has been excited by some star. And now the atoms are all excited. But these atoms, they stay excited, as I mentioned, just for a short amount of time. And then they remit that energy back in all directions. So if you have a telescope collecting some of that radiation, you are going to be able to detect an emission line. Absorption line is a little bit different. You have your star that is sending out all type of wavelengths: red, yellow, green, blue, violet, right? In fact, you have millions. You have all kind of frequency bands coming out of the star, and the cloud itself, um, and then you have between the source and your telescope, you have a cloud. You have a stellar atmosphere, or you have um, you have um, the gas in a galaxy. You have interstellar medium. You have all kind of things. So what happened is, of all these frequencies, look at this. The green was depleted. See the green here? The green is not there. The green is gone. So when you observe exactly where you would expect to have a green energy level or energy flux, you don't have it. It's gone. It's called absorption line. So these absorption lines, if it's too deep and too broad, it means you have a large amount of these elements producing absorption. And if it's too broad, it might be related to rotation, to all kind of things. So as a student, you learn to identify all these different features and explain them as the result of interaction of light with matter. And here, examples. So you have a spectral distribution with certain wavelength, and now you know this is a transition of hydrogen. This is another transition of hydrogen. Oh no, this is looks like sodium. I don't remember. No, this is not H beta. Sorry, this is not H beta 48. No, this is could be H beta. I'm right. This is H beta, H gamma, H delta, and here is uh, calcium, H and K line. So you identify all these transitions, and then you can, by analyzing and determining how deep they are, how broad they are, you can infer properties about the star. Okay, and I guess this is it for this chapter. So, oh, Harry is not there. So let me know if you need anything. I will send the email mentioning our exam and let me know how it goes. Take it easy.